15 minutes now, just doing a couple of notes and so on, about what we did last time and what we've done the rest of what we're going to do next, and then we'll spend the rest of the lesson kind of practicing and doing other bits and pieces. But just to remind you that we learned a little tiny bit about crude oil last time. I'm going to do more on what crude oil is when everybody's back, where it comes from, how it's formed and so on. But we learned that it's a mixture of hydrocarbons, and that was a key definition from last time. We said that they're covalent, simple covalent substances, molecules that are made of carbon and hydrogen only. It's a definition you need to learn, and we practiced that last time. There's two types of hydrocarbon, two families or two homologous series, which is a word we'll learn when we come back to organic chemistry next year. But these two families are the alkanes and the alkenes, and we're going to look at alkenes today. But alkanes, we said last time, are saturated. In other words, they've only got carbon-carbon single bonds. There are no double bonds, and that means that it's holding as many, or there are as many hydrogens as possible. So we learned to draw all of the alkanes from methane to pentane, I think. Well, we'll draw pentane if we haven't. So methane has got 1 carbon and 4 hydrogens. Ethane, 2 carbons and 6 hydrogens. Propane, 3 carbons, 8 hydrogens. We've got butane here, and this one is pentane. So this is butane, and that's pentane, pent with 5 carbons. And we also learned and have to learn that the general formula is CnH2n plus 2, or if you want to change it to X's, I guess you can. As long as you can work out that if we've got, say, 10 carbons, we end up with 22 hydrogens, right? And you've got to learn these prefixes, meth, eth, prop, but, pent, and the suffix ane to know that it's an alkane. And link that idea with being saturated, an alkane, and that general formula. Right, so we'll practice that in a bit, but you were pretty good at that last time. Today, instead, we're going to move on to looking at alkenes. I'm going to pass that back. We're going to look at alkenes, and this is another one of the families of hydrocarbons. So this is the second family of hydrocarbons we're going to learn about. And these are what we call the unsaturated hydrocarbons, or an example of an unsaturated hydrocarbon. So first of all, we've got to be clear what we mean by unsaturated, and that means that there are fewer hydrogens than it can in theory hold, which means that we're going to have a double bond. Now, there are lots of molecules in the world, and many others possible, that can have lots of double bonds and lots of carbon-carbon double bonds. But at GCSE, we're learning about molecules that have got 1 carbon-carbon double bond. So we call that a carbon-carbon double bond. So all the examples we're going to see at GCSE, we've got 1 carbon-carbon double bond. So because there's 2 carbons, it's not possible to have methene, is it? Because meth means 1 carbon. So the first in the family is ethene, which has got 2 carbons, this time only 4 hydrogens, because remember that carbon always makes 4 bonds. Hydrogen only makes 1 bond. So the only way to draw ethene, the double bond present between the 2 carbons, is to have 1 hydrogen on each corner, if you like, or 2 hydrogens per carbon. So like so. So that's ethene. And we'll practice drawing that shortly. So it's C2H4. You also have to be able to draw propene, and we can draw that like so. Now this is one that people often struggle with because you've got a different number of hydrogens attached to each carbon. The way to remember it is that you've got 3 carbons, and one of those carbon-carbon bonds is a double bond. And if we remember that every carbon always makes 4 bonds, if I can just get you to pause for a second and just look up. Every carbon makes 4 bonds. So this carbon, before I put any of the hydrogens on, this carbon had 2 bonds already made. It needs to make 2 more bonds. It will always make 2 more bonds, so it has to have 2 hydrogens. Now, the one in the middle is the one that people always get wrong. Look, there's 2 bonds here and 1 here. So it's already got 3 bonds being used up, but it's bonding to carbon. And so there's only 1 more bond, and that makes that bond to hydrogen. So don't be tempted to draw a second hydrogen off the middle carbon there. And then the last one is a bit like on alkanes. There's 3 spaces left, if you like. But let's draw a couple more. Let's draw a version of butene. And again, we can work out how many hydrogens on each carbon just by counting the number of bonds that each carbon makes really carefully. And I may be pushing beyond what we need to know for GCSE here, but it's a bit of fun. You can put the double bond between the middle 2 carbons and you end up with quite a different looking molecule. It doesn't matter at GCSE, by the way, whether the hydrogens are above or below the double bond. That's fine. So butene can be that, or it can be that. We learn they have slightly different names at Key Stage 5. But GCSE, you can have butene that's like that, and that is fine. And you could work out what pentene or hexene other ones would be if you needed to. I'm just going to pause it for a sec. I'm going to ask you to work out what the general formula is this time, and then we'll see if we can remember what the tests for those 2 different hydrocarbons were as well, and we'll write those down. So the general formula is always that. So if you had, for argument's sake, 10 carbons, you would have 20 hydrogens. You know that without even bothering to have to draw it. And the next thing we'll think about is the way that we test for alkenes and alkanes. So we'll go through that again, but I'll just practice it with you now. So it seems that your memory is a bit shaky with this, which is unsurprising because we've only seen it once, but you do need to know a whole load of different chemical tests for the GCSE chemistry course. So eventually we'll do a whole load of tests like flame tests and some others, but one test you need to know from this topic is how to distinguish between alkanes and alkenes. And in particular, we learn that alkenes, because of the double bond, because of their reactivity, they do something that alkanes don't do. Alkanes are really boring molecules. All you can do is burn them. Burning them is really useful, as we'll learn, because you can use them as fuels to power cars and that kind of stuff. But alkenes have got that double bond, and that makes them reactive. So let's make a note there. Double bond means they are reactive, or have more reactions they can do. And so that's the one that gives the positive result in this test. And what we learned, you might remember, is that we added some bromine water and then we shook it. So we say in the exam, we say shake with bromine water. And all bromine water is Br2, bromine dissolved in water. Right, so not a very complicated name. So shake with bromine water. If an alkene is present, that's ene, alkene is present, and you have to get this exact language. The bromine water turns from orange to colourless. Colourless, not clear, but colourless. If an alkene is present, the bromine turns, or the bromine water, if you like, turns from orange to colourless. Now you might remember, this isn't super important, you certainly don't need to know this for GCSE, for now at least. We'll, to be fair, we'll come back to something like this next year. But what's going on there is that when you react the bromine with the alkene, what you end up with is a bromine ending up on each of the carbons. And so the bromine essentially has been used up. So this was orange, and then it's gone, so it's no longer orange. So that's the reaction that's taking place. But these chemical reactions of what we call organic molecules, molecules that containing carbon, we'll spend much more time on next year, once we've done much more of the course. And this is colourless. So you have to shake with bromine water because it's in two layers. You've got the hydrocarbon on top, the bromine water underneath. You give it a shake, the bromine disappears, the colour changes. You also have to be aware of what happens if an alkene is not present, so we might as well write that down as well. So if no alkene is present, or if alkane is present, then the bromine water stays orange. So next lesson, we're going to talk about the combustion of hydrocarbons, what the products of combustion are. We'll do a little bit of practical work on that. We'll write that up next time. But for the last little bit of the lesson, we're going to look at the formation of crude oil, and we're going to watch a video which I'll post on the Google Classroom about the formation of crude oil, where it comes from, how it forms, and we may well write that up in a minute as well. So just a tiny bit then on following on from that video on the formation of crude oil, and we'll spend a whole lesson looking at how crude oil is processed through a process called fractional distillation, and then we'll look at cracking. But you have to have an understanding that crude oil, first of all, how it was formed and what it is, right? So crude oil is a mixture. In other words, it can be separated. That word mixture we learnt back in Key Stage 3. This idea of a mixture being substances that are not chemically bonded, so it can be separable. It's a mixture, so it can be separated. By a process that we'll learn about in another lesson called fractional distillation. Of hydrocarbons. There's a really thick, black, gloopy, gungy, messy stuff in it. All sorts of mostly alkanes that we need to separate up. And all of those alkanes are of varying length, some of them very short, some of them very long, and a bunch of other stuff in there as well. On its own, it's not much use. We have to separate it. We'll learn into what we call fractions that can be used, for example, as petrol. We have to understand, though, and this is the bit I wanted to cover now, that it was formed over millions of years. That's the first kind of idea. From the remains of organisms that lived, and as you saw from the video there, this could be plants, it could be little creatures, those diatoms that you talked about, and the remains of organisms that died millions of years ago. That's the main point, I suppose. But it's a good idea to have in your head a sense that those creatures died, and they would have, say, sunk to the bottom of, like in the video there, the bottom of those swamps or whatever it was, and put under enormous pressure and high temperature. And there would have been a lack of oxygen as well. And eventually, the remains that were there turn into crude oil, right? Which is then drilled from the rocks that it's trapped in. You don't need to know how that process works. If you can find out if you want to, but they use a process of drilling to get the crude oil out. Unfortunately, we're using it pretty fast. We're burning it quite a lot for all sorts of reasons, to powering power stations, for driving cars, for running all sorts of systems, and therefore it's going to get used up. And it's also, we're going to learn when we talk about the combustion of crude oil or combustion of hydrocarbons, producing carbon dioxide, and causes other problems when we burn it too. But I want you to have this sense for today. I just want you to have this sense that it's creatures that died millions of years ago, and they were squished under high pressure and high temperature for a very long time, with a lack of oxygen, and eventually you end up with this mixture which we're now using today. And I think that's a pretty good place to pause what I'm doing now, sort of stop that,